Assalamualaikum and a very good day to our lecturer, Miss Fatina Dira. We are Group 3 and today we will be presenting to the topic Associative Cache Memory Organization in any multi-core computer architecture, which is part of our subject Computer Organization and Architecture, CSC 429. This is our group members, which is start with me, Nur Shazwandi binti Muhammad Shafizal, 2024-6X1-5X6. And next one is Iman Hakimi bin Muhammad Nazmi, 2025-114-709. And the last one is Hana Humaira binti Kamaruddin, 2025-177-283.
In our discussion on a critical aspect of computer architecture as introduced on this slide for our course CSE 429. So let's jump to introduction. As the slide points out, in modern computing, especially with the multi-core processor that power everything from our laptop to massive data center, speed and efficiency are paramount. To solve this problem, we use cache memory. As stated here, cache is so small, extremely fast and more expensive type of memory that is located very close to the CPU. Its entire purpose is to store copies of data from the most frequently used main memory location. Because the cache is so close and so fast, the CPU can access data from it almost instantaneously, which dramatically improves the overall speed of the computer. However, as the slide correctly mentioned, simply having a cache is not enough. The real challenge lies in how we manage this small, valuable space. So, the performance benefits of a cache depend entirely on how data is stored and, more importantly, how it is searched for. A poorly organized cache can be inefficient, forcing the CPU to go back.
Next, we will diving into the topic of cache organization in computer system. There are three main types of cache organization, which is direct mapping, set associative, full associative. Each of these methods offers different levels of flexibility, speed, and complexity. Let's begin with looking at the simplest form, direct mapping. The direct mapping is the most straightforward cache organization technique. In this method, each block of main memory maps to exactly one block in the cache. That means a specific memory location has only one place it can go into the cache. This placement is determined by a fixed formula based on the block's address as shown in the diagram. Because of its simplicity, direct mapping is fast and easy implements, but it can lead to more cache misses compared to the another method, especially when multiple memory blocks compete for the same cache line.
Next, I'm going to briefly explain the concept of set associative mapping. Set associative mapping is basically a combination of two cache mapping techniques, direct mapping and fully associative mapping. It combines the advantages of both, giving us balance between flexibility and efficiency. In set associative mapping, if you look at the diagram here, you can see how the memory blocks are divided and mapped into different cache sets. Each set has multiple lines or slots where the data can be stored. This flexibility reduces the chances of cache misses compared to direct mapping.
Hi everyone, it's me again. Today we're looking at the fully associative cache. So imagine your computer memory is a big warehouse and the cache is a small, fast shelf right next to you. So in a fully associative system, so any item from that big warehouse can go into any empty spot on your fast shelf. So there are no rules about where it has to sit. It can go anywhere. There's a space. This makes it very flexible and efficient for quickly finding what the computer needs. There's a fully associative cache, total freedom for data placement. For a key reason why your computer feels fast, associative cache memory, we will use the AMD Ryzen 5 5600X as our example. So the CPU is excellent at handling data quickly, and it is all thanks to how it organizes its internal brain. Its cache memory, the Ryzen 5 5600X, actually use the three smart ways to do this. So let's quickly look at these three methods. So first, direct mapping. Think of it like a crystal ball predicting the future. What it does, it helps the CPU guess what instructions it needs next, like with the branch target buffer. By predicting, the CPU can grab data before it is even asked for, making things incredibly fast. Next, fully associative organization. Think of it like a super smart GPS. It is used in the TLB, which is translation look aside buffer. This quickly translates a virtual memory address into a real one. Like a GPS, it instantly finds where data is stored, no matter where it is, keeping memory access super quick. And the last one, finally, set associative organization. Think of it like an organized library with a few specific shelves for each topic. Where it goes, this is for the main data storage areas. So the L1, which is the 32 KB, and L2, 512 KB, catch. It balance speed and flexibility, allowing the CPU to find frequently used data very quickly. This is crucial for overall smooth performance. So, in short, the AMD Ryzen 5 5600X achieved its speeds not just by the raw power, but by intelligently using associative cache. It combines direct mapping for a quick prediction, fully associative is for rapid address lookups, and the last one is set associative for efficient data access. So, this brilliant combination means your CPU gets the right data, right where it needs it, leading to a much faster and more responsive experience.
Now, we will look at a real-world example of a device that uses this principle using Ryzen 5 5600X, the Skytech Shadow Custom RGB gaming PC. This system features is Ryzen 5 5600X CPU, RTX 4060T, 16 gig DDR4 RAM with RGB lighting. Why showcase this system? Because the Ryzen 5 5600X is a great example of a modern processor that is effectively utilizes cache organization techniques like direct mapping to boost performance. This system highlights how the Ryzen 5 5600X remains a popular, powerful choice in both custom and reboot PCs. This CPU holds its own in a real-world scenarios, which is play the gaming at a high settings or multitasking with a creative apps.
Going through the advantages and disadvantages of the three cache mapping types. Firstly, direct mapping. It's the easiest and cheapest type. It's also quite fast because it only checks one place, but the problem is it can have low performance because data can get replaced easily when many blocks compete for the one same spot. And next is fully associative. It's fast and simple to use. You can put data anywhere in the cache, but it's much more expensive because it needs to store extra information like the full address. And lastly is the set associative. This one gives better performance than the other two because it's much more flexible. But the downside is it's the most expensive because as the set size gets bigger, the cost also increases.
Hey, it's me again. Alright, to wrap things up, think of the cache memory mapping as the computer's secret weapon for speed. It is how your CPU gets the data it needs, super fast from the main memory into its quick little workspace. So, we learned there are three main strategies for this: direct, associative, and set associative mapping. So, each one has its own clever way in organizing data, but they all share the same goal to deliver information to your CPU for smooth, fast computing. So that's it. That's the big picture of a cache mapping. Thank you.
Memory organization in any multi-core computer architecture, we include the introduction, organization, summary, and references. And then moving on to the introduction, generally explain, it's in example in modern computers, especially those with multi-core processor, speed and efficiency are super important. So one of the key components that helps improve speed is cache memory. But just having cache memory is not enough. So how the data is stored and searched inside the cache plays a big role in performance. Then there are the three main types of mapping, which direct mapping, fully associative mapping, set associative mapping. In organization, let's look in figure 2.1 AMD Ryzen 5600X CPU as an example. This CPU uses a combination of all three mapping techniques, which in direct mapping, small fast structures like the branch target buffer and prefetch buffers are used to predict instructions quickly. Moving on, while fully associative mapping, the Ryzen CPU uses TLB, translation look-aside buffer, to map the virtual to physical memory addresses. And sets associative mapping, which Ryzen uses L1 cache, which 32 kilobyte, and L2 cache 512 kilobyte for fast and efficient data access. Thus, we can also see this technology in action in gaming systems like the Figure 2.2 Skytech Shadow Gaming PC, which uses the Ryzen 5600X paired with powerful graphics and fast memory. This system shows how the Ryzen series is still widely used in modern PC builds, whether for gaming or multitasking. And lastly, the summary. So in conclusion, in modern computers, cache memory plays a huge role in improving speed and efficiency, but the organization of the cache is just as important as having the cache itself. Then the combination of direct mapping, fully associative, and set associative mapping helps the systems like Ryzen 5000 series.